Okay, so we are live now on Facebook. Recording is on.
Good afternoon, everybody.
Good afternoon, sir.
Good afternoon, Vicky.
Namaskar, Sharma sir.
Good evening, sir. Good evening to everyone.
Good afternoon.
Sharma ji, namaskar. Can you
Namaskar.
just
Namaskar,
check
sir. Namaskar. I hope I'm audible.
Yeah, you are audible,
Absolutely.
sir. Can we just play your presentation? Can you just check if you can play?
Yeah, I'll just share it.
No, 4 o'clock.
That's okay now, I think.
Yes, sir. Perfect, sir. So you can just try it out and pull it off, sir. Then this is also tested.
Vicky, you're looking handsome.
Thank you so much. My voice was on mute. Actually, I couldn't respond. I was a little flummoxed by your.
I had to look 3-4 times before I could finally say, okay, oh, this is the guy. So, yeah, looking nice.
Thank you.
Sharma ji, you can stop sharing now.
Okay, sir.
राय साहब कहाँ हैं? Neeta, are you there?
We are what, 52, 53 now at the moment.
So we are live on Facebook. There was a poll on Facebook also, which I filled up, the same one.
Okay.
So we'll have poll on both sides.
Rai Sahab aa gaye. I just admitted him. Good afternoon, Rai sir.
Good afternoon, ji. Good afternoon.
भाई साहब आपको मैंने वो रीनेम कर दिए हैं
क्या
क्वेश्चन मार्क
ईमेल?
नहीं रीनेम किया सर आपका
Your name in the participant list.
That name is appearing changed on his icon also.
The 70 so far.
My suggest don't and let anyone enter before it's 4 o'clock. And meantime, you can check up your mics, etc.
No, सब check हो गया sir. Before you joined, we have checked the presentation, mics, and 70 people already entered, sir. We already have 70
I
people.
can see that 71.
Yeah.
But what I'm saying is we should do minimum talking once people are in.
We are not started, so just ठीक है, whatever.
Mera, the 7 questions you sent where?
कौन सा सर रीनेम किया है आपको क्वेश्चन मार्क के साथ आपके फोटोग्राफ में देखिए ना पार्टिसिपेंट लिस्ट में देखिए आपका क्वेश्चन मार्क आगे आया है since you will be collecting and collating the questions.
Sanjay, we can see how many people are there on Facebook also. कितना लोग है उधर already?
74.
नहीं Facebook पे.
Guys,
Mera, do tell people who are sending questions or chat to put a question mark after they return.
so your name has been changed to question mark.
No, I know that. Yeah.
And but the problem is everybody. I think David will announce that, but everybody tends to ignore or in the hurry mark it to everybody these questions. So you might get some on your personal and some you might have to pick up from the common one.
I will be, yeah. David, should I send questions to your personal list में या seminar वाले में?
Seminar में भेज दीजिए sir, no problems. जैसे भी मर्जी हो, I have no problems.
I think seminar would be better because if anybody has to communicate with me also,
Okay.
it will become a little problem. Seminar one we are using.
Yes.
Pulpit sir, let me know when you want to start.
जैन साहब कैसा करना है?
We can start.
We have 119, 120. We'll start, sir. We'll start.
4 o'clock. Yes, I think we can start.
Okay. Sanjeev, I'm starting.
Yes, sir. Please, sir.
Hi, everyone. It gives me great pleasure to welcome you all to the Institute of Marine Engineers India Mumbai branch's first online technical training session. The topic chosen being NDT, non-destructive testing. Of course, as marine engineers and others who are concerned with this, we are well aware of the importance of this, and hence I'm sure you all are eager to hear from our expert on this subject matter. So without much delay, let us start. I would like to request Mr. Vijendra Jain, Chairman of the IMEI Mumbai branch, to commence the proceedings. Over to you, Mr. Jain.
Thank you, David. Shri A.K. Sharma, members of the Marine fraternity who are present here today, ladies and gentlemen, colleagues and friends. Good evening and a warm welcome to this NDT awareness program on principles and application of conventional NDT methods. Something which is very close to my heart and which is being brought to you by the Mumbai branch of the Institute of Marine Engineers India. We are indeed humbled and encouraged by this tremendous response for attending this introductory lecture. Ever since the lockdown was thrust upon us on 23rd of March, all of us in the branch started thinking as to how we need to adapt to this new situation, or rather the new normal. At first, we wished it was temporary and would disappear soon. However, within a short period of time, we realized that this problem is not going away. We became more serious in our efforts, and it took us almost about a month to be able to put into action what we were planning for a long time. On 25th April, we organized our first webinar, which was attended by over 700 people. Thereafter, our dynamic technical meetings and seminars committee under Mr. T.S. Girish organized another conclave on 16th of May, which was organized jointly with the CMMI. Not to be left out, our Social Initiatives Committee, under the ever enthusiastic Mr. Sanjeev Mehra, organized a yogic meditation session on 2nd May and followed it up with a hugely popular Antakshari program on 24th May, which has had over 1,000 hits on Facebook. Almost as if taking a cue, the Training Courses Committee has organized this lecture today, which has had over 400 registrations. This, together with a number of persons who view the live proceedings on YouTube and Facebook, means we shall have an audience which is about 10 times more than what we normally have for our physical lectures. They say necessity is the mother of invention, or every adversity brings in an opportunity. These sayings could never be more true. Although non-destructive testing is a vast subject which extends across the industry, our guest speaker tonight, Mr. A.K. Sharma, is no freshie to the maritime industry. He worked in IRS for a number of years in the Mumbai office, where I had the good fortune of interacting with him. After we hosted a function at the Hilton in December last year, announcing our intention to hold classes, he got in touch with me, and after rounds of discussions, we organized a physical lecture on 21st March on the same very topic, which unfortunately had to be abandoned due to the virus. Although now we are over 2 months late, we are still very happy to have converted this physical lecture to an e-lecture and have you all here with us. Non-destructive testing is a very vast topic and consists of a number of subjects within a subject. Magnetic particle test, radiography, ultrasonic testing, liquid penetrant testing, visual testing are all some of the forms of NDT. By far, the most common method used in our industry is ultrasonic testing. Even as late as the 1970s and 1980s, people were worried about corrosion and thickness plates on ships. A surveyor would go about hammering at places which he felt were suspect, and by the interpretation of the sound, make his decision. whether to remove, whether
Yes.
to cut a plate, have a plate renewed or not. In some cases, holes were also drilled in plates to ascertain the corrosion levels. In 1993, IMO felt the need and came out with the rules and regulations for thickness measurement on ships, as well as close-up surveys which need to be taken on ships. There were four broad classification of ships, that is bulk carriers, tankers, cargo ships, and any other ships. Any other ships would mean OSVs, tugs, etc. IMO specified the areas to be gauged on each of these four types of ships and the periodicity for the gauging. Since 1993, these rules have largely remained untouched, save for a very few changes in bulk carriers, which had a number of accidents. And so there were some additional requirements with regards to cargo hold number one, the inspections done there. UTM, that is ultrasonic thickness measurement, has been the most common forms of NDT employed on ships, and for years, classification societies have been giving companies approval for carrying out this thickness measurement on ships. However, from this year onwards, there is recognition that firms carrying out other forms of NDT will also be approved due to a growing need of these forms of testing as well. As I was mentioning, after 1993, it became mandatory for everyone involved in thickness measurement to have what we call a through thickness gauge, which worked on a multiple echo principle. In short, an operator could take readings on moderately corroded plates without having to chip and grind the parent surface. In other words, one did not have to remove the paint in order to take the thickness and therefore be environmental friendly. So these are the various changes which have occurred over the years in this field of thickness measurement. The challenge that COVID-19 has imposed upon us is how do we handle practical aspects of NDT in an online class? However, it does not stop us from organizing these theory classes online, which are equally important and equally knowledgeable. The IMEI intends to start classes on a paid basis similar to the electronics and hydraulics courses to educate and allow its members to gain expertise in this subject. We shall, in our questionnaire at the end of the session, take your feedback as to whether you would be interested in attending such a class and gaining such a certification. With these few words, I leave the floor open and request our very experienced and dedicated technical classes head, Mr. David Birwadkar, to take this session forward. Thank you.
Many thanks, Mr. Jain, for all the encouragement. And you have given a good insight into into entity, which is now going to be the topic of the day. So it's a lovely platform to start off with. So now shifting focus to the topic of the evening, it gives me immense pleasure to introduce our presenter, Mr. Arvind Sharma, who is an authority on this topic. His credentials give ample proof of the same. Mr. Sharma completed his Master's in Engineering in Metallurgy from MS University of Baroda in 1983. His professional qualifications include ISO 9712 NDE Level 3, ASNT NDT Level 3, Diploma EWE/IWE from TWI Cambridge, UK, IRCA registered QMS Principal Auditor. His professional affiliations include life member of IIW, ISNT and IIM, member of ASNT, past vice chairman IIW Mumbai branch from 1999 to 2004, past committee member of BIS for welding, pressure vessel and structural steel committees in 2002-2003, life member and chartered member of Institute of Engineers, India, past approved pressure vessel inspector by Ministry of Manpower, Singapore, past approved pressure vessel inspector by Chief Controller of Explosives, technical expert for Dubai Accreditation Council for ISO 17020, and presently committee member of ISNT Mumbai branch. His career history worked from 1984 to 1990 in Mazgon Docks in quality control and NDT of offshore platforms and jackup rigs of ONGC. 1999 1990 to 2005, that is almost 15 years in IRS as senior surveyor for inspection of marine and industrial components, providing training in metallurgy, welding, and NDT to surveyors, inspection systems development, and ISO 9001 credit certification audits. 2005 to 2007 with Bureau Veritas as operations managers in Dubai and Mumbai. 2007 to 2009 with ABS as head of operations in Kuwait and Mumbai. 2009 to 2016, he worked with Petrofac in Sharjah. And 2017 to 18, back with IRS Industrial Division as divisional head, QHSE and risk. 2018 to December 2019 with again Petrofac International Sharjah as project quality manager for HPCL's Vishaka refinery modernization project. And now he works as a freelancer and consultant for QA/QC, welding, NDT, supplier assessment, etc. He is founder of the Quality Consulting and Training Services. With such amazing credentials, it is but appropriate that we have requested him to train us on this topic. I request you to send all your questions to the designated person on chat marked as question mark so that they are not missed. And so now, without much ado, over to Mr. Sharma.
Thank you, Mr. David, for elaborate introduction. And thanks, Mr. Jain and other senior members for giving me this opportunity to present share my experience on NDT. And I would like to now share my screen with you. 1 minute. Mr. Jain has already provided the insight of what since 90s was the time when I had joined IRS, and from then onwards up to 2005, I was really involved in, apart from other activities, NDT was one of the key activity which I used to take care of. Now in this presentation, I'm covering only the basic methods which are most widely used in marine industry and also in other industry. And these basic methods are penetrant testing, magnetic particle testing, radiography testing, and ultrasonic testing. There are actually, as per ASNT, there are 16 NDT methods, which are very, very elaborate and going deep into the subjects like neutron radiography. In radiography itself, there are 3-4 type of NDT methods, but we would be dealing with what we normally practice during our day-to-day life. Now, as Mr. Jain had pointed out that each subject is a very vast subject in NDT. Each method is a vast and everything cannot be covered in such a short time. But what I would be doing is I would briefly, maybe what you already know, it would be refreshing your minds with basic knowledge about each method. And then I would be mentioning what generally is followed in code as a good practice. And for each method, I have got one slide, which is a very important slide, which summarizes everything and talks about what we should remember while we are either inspecting an NDT component or we are carrying out a survey or supervising NDT. So with this, I will first start off with the penetrant testing method. Penetrant testing is the most, I would say, ignored NDT method, where people think that it's very easy and anybody can perform NDT, and it's happening also in the industry. If you see that we just want to witness a PT, we don't care about who is doing and how it is being done and all that. But it is not really so easy. You have to follow certain steps which are very critical, and if you don't follow those, you are likely to miss defects, and your outcome may not be as what you would be expecting. So penetrant testing has been being done since many years, and long ago, now also railroad components are being tested by MPI. There are so many applications of MPI. I will not go into details of each, but in marine industry, it's famous, like even now people must be doing this kerosene and chalk test, like to check the leakages of tanks, where you clean the surface of the weld, and then you apply kerosene from one side, and after some time you apply chalk powder on the other side to see whether there is any dampness, and you can check whether tank is leaking or not. With the same is the principle with penetrant testing. Now, the penetrant testing materials which are used, mainly they are very combustible materials, and one need to take care about their storage and handling, because if they are open to smokes and flames, they are likely to catch fire. So it is always better to review the material safety data sheets of the materials, and as a precautionary measure, follow all the instructions with respect to the storage and handling of these materials. Though it has got a penetrant kit which contains a cleaner, a penetrant, which is a dye, and a developer. So this technique normally is applied to detect surface and subsurface defects, and the subsurface defect should be open to the surface. If it is not open to the surface, then you will not get any indication in penetrant testing. So that is one of the things that you have to keep in mind always. And this is also widely known as a dye penetrant test or a liquid penetrant test, but ASNT terminology, we call it as a penetrant testing. Now it has got 5 basic steps, as you can see, and I will explain. The first one is that we need to clean the surface. Cleaning has to be very, very proper to ensure that all the dust and oil and foreign material is removed, and the cavity which we are expecting it to be a defect, it should be very clean. And after cleaning is done thoroughly, then you have to apply the dye, which we call it as a penetrant. And this has to be also, various methods are there how to apply, which we'll be seeing in the other slides. Once dye is applied, you have to hold for some time, what we call it as a penetrant dwell time. Dwell time is the time where we allow that dye to enter the surface of the cavity or the crack or whatever defect we expect. And then once it has entered the entire through cavity, then we remove the excess penetrant. That the next step is removal of the excess penetrant which is there on the surface of the test that you are conducting. It could be weld or other surface. Again, this requires a bit of a technique how to do it. Otherwise, if it's not done properly, again, there are chances you might remove the entire cavity, the penetrant which has gone inside the material. If you do it rigorously and over a long period of time than it is required, then you will be removing all the penetrant which has come out, which was there in the defect. Finally, once excess penetrant is removed, you have to apply the developer, which is a white spray mixed in an aqueous liquid, a kind of a powder, which once you apply through an aerosol can, it is volatile part gets evaporated, and what remains is the white powdery part. Once it is dry, you will be able to, in the meantime, we call it as a developer dwell time. After about 10 minutes, the indication starts forming, and the penetrant which was there inside the cavity will come out in the form of an indication which can be interpreted. So these are the basic 5 steps. Now we'll see a subsequent slide what is important and what we tend to miss out in this. But before we do that, we will see certain techniques that penetrant testing can be applied. One is the visible method, which is simple, like we are not using any fluorescent lamp or anything to detect the indication. After the penetrant is applied, we check it to the naked eye, or once in a while for a magnifying glass, which is not very high magnification, maybe 20x or so. And then that indication is that is called a visible solvent penetrant process. Whereas the other one is a fluorescent MPI. What you see in this slide, the pictures that you see is a fluorescent technique where you have a penetrant which will have a fluorescence, which the indication, if it is seen under UV light, it will glow and it will fluoresce. This technique is generally applied on machined components and where the sensitivity requirements are high, where you are expecting tight fatigue cracks and such defects. There we go for a more sensitive method, which is a fluorescent dye penetrant testing. So this we have seen now for penetrant testing what is required. We need to clean the surface, apply the penetrant, then the solvent, we clean the excess penetrant and apply the developer and carry out the interpretation. Now dwell time is important from Penetrant dwell time as well as developer dwell time. Penetrant dwell time is generally for wrought materials, it is specified as 10 minutes. But for other materials, for castings and all, it could be 5 minutes. And for each material, the section 5 gives you what are the dwell times required. But generally it is 10 minutes and 5 minutes. For our application, most of the time it is 10 minutes. Similarly, dwell time of developer also is 10 minutes minimum. And then you can do the interpretation up to 1 hour as per section 5. Now, as I was saying, you can apply the penetrant in a number of ways. That is by spraying. Spraying is generally what the kit I had shown in the previous slides. We have aerosol cans where you can spray the penetrant. Or it can be also applied by brushing, pouring, or dipping. The important what we should understand is that whatever method or the procedure we have followed as a documented and approved procedure, the same procedure we need to follow in subsequent tests that we do. If I have approved a procedure where the spray is used, then I should follow that only during my penetrant testing. If I change these variables, I have to prove again that yes, what I'm doing is correct and I'm able to detect the defects which I'm supposed to pick up. These are some just pictures only, which the other requirement here is that for visible method, you need to have minimum lighting as specified in the code, which is 1000 lux. 1000 lux should be minimum lighting at the time of evaluation and interpretation of the indication. If you're doing a visible method, it is 1000 lux. If you're doing a fluorescent method, it is 1000 microwatt per centimeter square. Now for fluorescent method, you need to have a UV light and the lux meter, what we call it. Oh, sorry, yes. Black light meter, which will measure the quantity of the lighting which is there, UV light intensity. When you're doing a fluorescent test, it is also important to see that apart from 1000 microwatts per centimeter square UV light intensity, you make sure that there is no leakage of white light from any of the darkened area that you have made for doing fluorescent MPI or fluorescent PT. So the leakage up to 20 lux is permitted as per the code. If the leakage of white light, that is normal light, is more, then you have to prevent and take care of that leakage light. This is how you check. Generally, when you're doing a penetrant examination, you're supposed to measure 1000 lux. Now, everybody may not have the lux meter with them. So what the codes specify is that at least you should be able to once measure what is the intensity of the light that you're having for carrying out the PT examination, and keep that as a record of measurement with you available at all the time. If anybody you are suspecting anytime, you have the measurement. And how you do that is, suppose you have a say 30 watt or 40 watt bulb, which is kept at a meter. There you hire a lux meter and check what is the intensity. And if you're getting minimum 1000 lux, then you know that by using 30 watt bulb at a 1 meter distance, I'm able to get that minimum lighting that is required. So that you have it in your file established, and then you can carry out the PT examination accordingly. You don't have to use lux meter every time. So this is the meter which will check you the white light intensity it will give. Now the interpretation and evaluation. The interpretation is first you have to see whether what indications you have got, whether it is a relevant indication or a non-relevant indication. That means really it is coming from a defect or it is coming from the process that you are not carried out properly. It is because of that. So evaluation would be once you have established that yes, it is a relevant indication, then you have to evaluate against your acceptance norms or against whatever code you are following, whether that relevant indication is meeting your requirement or not. And most of the codes, they will, at least for penetrant testing and magnetic particle testing, they will not accept any linear indication. So rounded indications like porosities and all, there are acceptance given, say 5 mm isolated spot can be accepted and things like that. But linear indications in PT as well as MT, they are not acceptable. As I said, there could be false indications, non-relevant and relevant indications. Many times false and non-relevant, we put it in one category only, like a non-relevant indication. And then we have relevant indications. And also we should understand that a linear indication is one which is having a linear dimensions at least 3 times more than the your shorter dimension. And a rounded indication would be one which is having a longer dimension less than 3 times the shorter dimension. Now again, if you found a discontinuity could be a defect or could not be a defect. Now discontinuity, you have to evaluate against an acceptance norm. If it is not meeting as per your service conditions for that particular application, then it becomes a defect. And if it is meeting the acceptance criteria, then we leave it as a discontinuity and we accept, or we use it general, we are used to using a term defect only. So let's call it a defect which is acceptable and a defect which is not acceptable. The false indications can come because of various reasons. Some could be because the cleaning is not done properly. The cloth that you used is not lint free. It is having some threads and all, which will leave a penetrant and give an indication later on when you apply a developer. Penetrant, the technician's hands were not, he has put his hands, thumbs, impressions here and there. There could be various reasons of having a false or irrelevant indication. One should know about it so that during interpretation it becomes easy to make out whether it is a real indication or it is a false indication. Now, one thing we should see when it is a false indication is that it should not be masking the real relevant indication. If you have a false indication, fine, but it should not mask the relevant indication, otherwise you are going to miss it. Now, some indications which are false will appear like this, like you have tool marks, you have thumb impressions, patchwork like this, finger impressions like this, or coming from a dirty cloth, the impression can come, something like that. Non-relevant indication could be, it's a really an indication which may, if you're not aware of how the manufacturing of the component is done, you may interpret it as a defect, but it is not non-relevant. Like press fit parts will give you an indication where the press fitting is done. There you will get an indication because it is not totally fused. Riveted connections and spot welds, these are some of the areas where you know that there is going to be an indication which you should be able to interpret properly, that yes, this is not the defect I'm looking for. It is a part of the component that is giving an indication. As I said, relevant indications are those which are caused by the discontinuities on the test object, and all relevant indications may be defects. Now, seeing some of the penetrant kits which are available, they are, as I said, the 4 sets are there, which are cleaners and penetrant and developer. For fluorescent, you have portable UV lamps, and again, these 3 basic cleaners are there, and you have some tools for, and you may have some lux meter, UV light meter, and white light meter also for seeing that there is no leakage. Now, some advantages of penetrant testing. It's very easy to perform. We all know because it was the easiest method, and it detects the defects which are at the surface and close to the surface. And one condition, as I said, the internal defects or subsurface defects will be revealed only if the defect is open to the surface. It uses inexpensive equipment, as 3 containers. What we see is they are not very expensive, maybe 200 to 250 rupees each container, and we can perform the PT. Technicians can visually see the defects. There is no other equipment or something highly skilled required to see the defect. Of course, the skill is required to perform PT, and it can be used for raw material checks and in-service checks and final examinations of materials and components. As I said, this limitation is that all the defects should be open to the surface, then only it will be detected by PT. Otherwise, you will not be able to detect hidden or concealed defects. The guidelines for all the NDT methods are given in ASME section 5, which is a boiler and pressure vessel code. In section 5, it has got various sections, and section 5 is dealing with NDT. and various articles, different articles that dealing with different NDT methods. So Article 6 is for PT, which gives you the entire guidelines of how PT should be performed. Some of the requirements which I have listed, like minimum lighting requirements and cleaning and dwell times and all, they're all given in section 5, Article 6. And for the same ASME code, section 8 division 1 is the one which gives 8 division 1 is for the pressure vessels, and appendix 8 gives acceptance criteria for PT. PT which is performed as per Article 5, Article 6 of section 5. The acceptance could be as per section 8 division 1, article appendix 8. Of course, there are other acceptance standards also. I've just given an example which is most widely used. For walls and fittings, you have NCB 3116.34 also, which talks about acceptance norms for PT, MT, RT, and UT. They have given in the appendix for castings, forgings, and all that. Now, because this extract did not come very clear, so for each method, I have prepared what are the key points which we should remember while we are performing PT. It's a summary of all what we discussed, and the important things which we should not miss out during performance of PT are listed here. Intermixing of penetrant materials of different manufacturers are not permitted. The code doesn't allow that you have a penetrant of one manufacturer and a developer of another manufacturer, or I have a little left penetrant of one manufacturer, I add up a penetrant of the other manufacturers in that. These things are not permitted. It has to be of one manufacturers only. The minimum light intensity, as I said, has to be 1000 lux for visible method and 1000 microwatt per centimeter square for fluorescent method. Now, other important things which did not appear in the slide, but I mentioned here is minimum and maximum time lapse between the steps. This has to be established. For example, I do the cleaning of a surface before I apply a penetrant. Now, how much is the time I should give after cleaning before application of the penetrant? I cannot give unlimited time. I clean the surface now and I apply the penetrant after 2 hours. Maybe my environment is such that in 2 hours, I'm again spoiling my surface and we may not be good for doing a penetrant test. So these things have to be established as a procedure that, yes, if I allow half an hour time after cleaning, the surface doesn't get deteriorated, I'm able to still pick up the indication. Same, after you have applied the removed excess penetrant, how much time you should wait to apply the developer. So these intermediate steps and the minimum maximum time that may be required for performing from one step to the other is very, very important. Now, lastly, suppose interpretation. Interpretation code says has to be done after 10 minutes after the developer is applied, up to 60 minutes, up to 2 hours, you can wait and you can do the interpretation fine. But I have seen in practice many times people writing in the report that yes, the manufacturer performed the PT in morning and which was witnessed by whoever inspector has gone in the afternoon. These things statement doesn't carry any meaning. Either you accept what the manufacturer has done, or you don't have to say that you accepted after 2 hours. It's meaningless. Other thing is control of contaminants in the penetrant material. When you're using this penetrants method in stainless steel or nickels and these kind of materials, then you make sure your sulfur content in the penetrant materials is not more than 0.1% by weight. And if you're using on stainless steel, your chlorine and fluorides and all, they are not exceeding 0.1% per weight wise. Now, again, the test temperature is important. It says that you can easily do penetrant testing from 10 degrees to 52 degrees. That is the permitted by the code. But now also permitted is that you can go down from 5 degrees up to 10 degrees, provided your dwell time is doubled. You have established a dwell time for carrying out PT from 10 degrees to 52 degrees. But if you're doing it at, for say, 8 degrees, for which you have not established procedure, but then you have to ensure that your dwell time for 10 to 52 degrees was say 10 minutes. Now, if you're going down 10 minutes, your dwell time has to be 20 minutes. So these these things people do miss out, like a procedure made in Mumbai, and the job is being done in, it has happened with me, I have seen that in Chenab, somewhere in near to Kashmir, and then the same procedure is being followed, where in the winter the temperatures are going even sometimes below 5 degrees. So it's not that you cannot do, but you can do, but provided you follow the correct steps. Because the viscosity of the penetrant becomes high, and it will take more time to penetrate. That is why you have to allow extra time. Now these are the variables. Like as I said, final interpretation has to be done not less than 10 minutes and not more than 60 minutes after application of the developer. So that was about PT. Now we will go to the next topic, that is magnetic particle testing. Again, there are so many things in this, but we know what is magnetism and how we can magnetize the material and all that. So we'll not go into too much details of those. With the assumption that we know those things, we will move forward and try to discuss only what are more important and critical things while we are performing MT. Now, when you're magnetizing a part, you can generate either a longitudinal magnetic field or a circular magnetic field. And when there is a discontinuity, the flux that is introduced because of magnetism will be having a leakage at the points where there is a crack or opening, and the flux lines will jump over it, and when you apply a magnetic ink or a dry powder, it will get attracted because of the changes in the flux density that is formed. See, here you can see where there is no change in the discontinuities, imperfection, then the flow line, flux lines are moving smoothly. And where there is a leakage or a cavity, the flux lines get concentrated. We'll see in the next slides where you will be able to find a defect. So here also you have to do a cleaning of the part first before doing MT. Then introduce the magnetic field. There are ways and different techniques to introduce. Then apply the magnetic medium. Again, there are ways. You have dry method and wet method, fluorescent. Then do the interpretation of the indication that that has been formed. While cleaning, you have to ensure there are no contaminants. Mainly oil and grease are the main culprits which you find during the area where we are supposed to carry out PT, and that should be ensured that the surface is clear of the grease and oil and paint. Other things can be wire brushed and removed, but these things will not be able to remove. Now you have, sorry, you can do MT by using a permanent magnet, or using a AC/DC yoke, or by passing a current through the conductor, and you have coils where you can introduce magnetic fields. We will see one by one. But for all the things that you do, you have a dry particle or wet particle method, or you have a fluorescent and non-fluorescent method, and you have a continuous and residual method. Now we should understand what it is. Like dry and wet, we know, like there was in PT also. We have fluorescent, non-fluorescent also, we know what. Now continuous and residual, this we should try to understand. What is a continuous method of magnetization and what is a residual method of magnetization, and where to apply continuous and where to. Most of the application we would be applying only continuous method. Continuous method means that you are doing the interpretation while the magnetic field is on. You are magnetizing the part, you're not removing the magnetic field, and you apply the powders and see the indication being formed, and that is your interpretation. And after you have done that, then you remove the magnetic field. That is called a continuous method. Whereas a residual method would be, the part is very hard material which can retain magnetism, and you are magnetizing that part. Now, because of retained magnetism, you may remove the magnetic field. After that also, there is a lot of amount of magnetism is there in the material, and you apply dry or wet particles wherever there is an indication, they will attack and the indication will be formed. As I said, if you're doing on a residual method, you have to make sure that the system is working. You will have to see that, demonstrate to me that yes, you are having a good amount of magnetic field. Because I have seen in practice where you must be knowing that, pipes at the bevel end, they do MPI to make sure there are no exposed laminations. And when the pipes are produced in the mill, there is a standard practice that they do the MPI of the bevel end of the pipe by magnetizing the end and then carrying out the process. Now I've seen this process being done on plain carbon steel pipe, that is your standard pipe A106 grade B, and they are magnetizing the end, removing the field, and they are applying the wet particles and then seeing there is nothing and everything is cleared. And now when this was seen, you cannot accept this. I said, no, this is not the way you're doing. Then it was like, they've been doing this so many years. So I said, you get a Gauss meter and check. Once you're removing the field, now you check what is the magnetism. And with Gauss, when you check what is the magnetism, it is showing 0.1, 0.2 reading, like it is nearly zero. And when the part is not magnetized, you apply whatever amount of dry powder or wet powder, it is not going to form any indication. So mostly you should ask for a continuous method of magnetization. And somebody is doing residual, you have to be careful and make sure that residual method is appropriately being done. MT on a crankshaft, it's there are equipments where you have longitudinal as well as circular field generated in headshot method, they call it. And this is one of those kind of method where you magnetize the component through magnetic field, circular as well as longitudinal. Sorry, it's this one. You have current pads here, both the ends, which will generate a circular field, and then you have encircling coils, which will generate a longitudinal field. And in one set of magnetization, you can carry out the entire MPI and all types of defects, whether they are longitudinal or transverse, you will be able to detect those. Now, as you see, this is a longitudinal field, I would say, and this is a circular field. Now, if a defect is if you have a defect which is parallel to this line, then it's not going to be detected. Even if it is up to 45 degrees to these lines, it would still form an indication. But if it is less than 45 degrees, tending towards parallel to these lines, it will not form an indication. Here it is other way. A longitudinal defect you will be able to see, but a circular defect you will not be able to see because it runs parallel to the magnetic flux. So these things you should know which kind of method will generate what kind of field. And that is why for each MPI I will show in the next where there is a yoke, you will have a better idea. Like here, for this field, you will see a longitudinal defect, and this type of defect, which is across the circumference, will not be picked up in this. Now this is again generating a longitudinal field because encircling coil is there, and the field will be like this, and you can find out defect which are transverse to this field. Now here, this is the AC/DC yoke. What we are saying that is widely used in the industry. You must have seen also wherever MPI has been done. Your MPI NDT service provider will come with this kind of equipment, and they will do an MPI. As I was saying, the direction only 90 degrees and 45 degrees defects can be detected if they are in one direction of the field. That is why for at each location, you have to do this twice. Like, you have fix at one portion like this, you see whether the defects or not. And then at the same location, you turn the yoke 90 degrees so that the orientation of the field will be different. And then again, you try to see there are no defects. So at each location, you have to do twice to see that all kinds of oriented defects you are able to pick up. And this is what is called as a pi gauge, which is used to indicate the direction and the strength of the field. Once you have magnetized, you can have this introduced into the magnetic field, with these lines, lines, what you see, we just tend like crack-like thing. It should be upside down, and from upper surface, you after it is magnetized, you put dry powder or wet powder. Generally, it is dry powder, and you will see that these lines are appearing on the other side of the pi gauge. That means the field strength is adequate, and it's picking up these indications. So it may pick up the defect indication also. Circular magnetization, when you're passing current through the conductor, you will develop a circular field. And this is again a headshot method where you're doing MPI. The various combinations are there, but you should know what you're using so that you're able to pick up all the defects. If you're introducing a longitudinal field, you have to make sure you rotate the part by 90 degrees and carry out the test again so that even the transverse defects you're able to pick up. Wet part methods also, particles you can use, same. Now what generally for dry methods, you must have seen also, the NDT operator will first, if they're doing on the weld, they will put a white coat, and then over that they will magnetize and put a colored particles, either red or gray, which are mixed in a medium, and then where there is an indication, with a good contrast, you will get white and red contrast, and you will be able to pick up the indication. And that paint is hardly about 15-20 microns. So you should not be able to be worried about that there is a paint and over that they are doing MPI. Of course, if there is a painted surface, there you should not do MPI, because if there is a painted surface, then again demonstration is required. If the paint is up to 50-60 microns, no problem. If the paint is having more thickness, then what you have to do is take up a mock-up piece with the paint surface or with artificial defect, see that this defect is picked up under the paint, and then you can do the entire surface which you want to do, which is painted surface. For dry methods, you get dry powders with different colors on like this. Now you can make a mix also of wet particles by having some concentrations are available in the market, where you mix particles and then you rotate in the centrifuge for half an hour and see the settling velocities and all that. But easiest way is to use this aerosol cans, where again you have a cleaner and your wet particles which you can apply straight away. Very easy to maintain. But if you're preparing particles like this with the centrifuge and all, a lot of other controls are required, which we should avoid. Now, seeing the indications which are formed, all these are using a fluorescent method. In the hook tested with fluorescent, this gear tested with fluorescent, you can see a crack here. Again, very clearly you can see under UV light the indication that is formed. On the weld, on the edges, you can see there is lack of fusion in a SMW weld. There's manual welding. Here also you can see there is a toe crack, and there are some undercuts also you can see on this other side. Again, there are cracks at throat and toe of the weld. Now, you may require to demagnetize a part after the test has been done. May not be always, but certain applications would require demagnetization. If your subsequent operation is likely to be affected with the magnetic field, then you have to do a demagnetization. That means bring the part to the original condition by removing the entire magnetic field. And generally after demagnetization, the acceptable is, in pipelines, it is a 25 up to 25 Gauss strength of magnetic field is acceptable. But the best is, if you do not know how much to accept, up to about 5 Gauss you restrict, and you can do a demagnetize. For AC currents, when you're using, demagnetization is not required, because the AC itself, because of this type of current, will demagnetize the part. But again, here people claim that this is a method where you can do surface cracks detection is no problem. And for that, AC current is the best that you can use for surface crack detection. When you have to detect indications or cracks which are subsurface, then you have to, there are two things. One, you have to demonstrate that how much depth your system is going to pick up. Another thing is you have to use half-wave DC current. Like, neither AC will not work or a pure DC current will not work. You have to use a half-wave DC current, which gives a little mobility of the particles when you apply after magnetization. And that mobility will increase the sensitivity, and they will be able to penetrate the surface and form an indication. For any MPI, people claiming that yes, my equipment, I'm able to detect 6 mm below the surface or 4 mm below the surface. These are all claims. Let them demonstrate that yes, they're able to pick up 6 mm. Once demonstration is done, then you have more confidence that yes, the system is going to work. What are the advantages? We can detect surface as well as subsurface defects. May or may not be open to the surface, unlike PT. It can detect all type of defects irregular in shape, and pre-cleaning is, all this process is not very difficult to follow. Fast method for inspection and indications are visible directly on the specimen which you are testing. Very low cost compared to other methods which like radiography and ultrasonic testing. It's a very portable inspection method, especially when used with the battery powered equipment. Yeah. Limitations: you cannot detect on a non-ferrous. The materials which you cannot magnetize, you cannot test using MPI. And the most common material that we use is stainless steel, where we are restricted for this technique because you cannot magnetize stainless steel. Similarly, aluminum also in case. Inspection of large parts may require use of equipment with special power requirements. This could be a limitation again. With the coated surface, you cannot do MPI. As I said, you will have to demonstrate that process is working. Otherwise, you have to remove the paint. Sensitivity has to be established. People claim 6 mm below the surface you can do MPI, but unless it is demonstrated, it is difficult to accept. Post-cleaning demagnetization is many times may be required, which is an additional step which is required to be followed. Alignment between the magnetic flux and defect is important. That means how you magnetize, whether you are looking for transverse defect, then you have to introduce a longitudinal field and vice versa. Again, going a little, what important things are there in this? What is my magnetizing technique? How I prepare my surface? These are all essential things which we should follow. And once we have established, we follow the same technique. Method of magnetizing the part, whether it is by yoke. Now yoke, when you're using, the AC yoke will have a lifting power of 4.5 kgs. You have to demonstrate like, calibrated weight. If it's able to lift 4.5 kg, means it is having good strength to be operated as a AC yoke. Similarly for DC, it is 18 kg. It has to lift 18 kg at the maximum pole spacing. Then it is having a good strength. Minimum lighting for visible 100 lux, and for fluorescent 1000 microwatt per centimeter square. Empty and coated surface demonstration is required, is recommended, I would say. You should not go without recommendation, without actually doing a demonstration. Examination of the parts. Generally, dry particles you can use up to 316 degrees centigrade, because they are basically metallic iron particles. So you can use up to high temperatures. Whereas wet particles, generally recommendations are up to 52 degrees centigrade, because they are in a liquid which is volatile, and sometimes kerosene and things are used like that. And we have to make sure that whatever is the recommendations of the manufacturer, we have to restrict the temperature as it is recommended by the manufacturer for the wet particle method. But definitely not advisable to go beyond 52 degrees. So that was MT, and next topic that we have is radiography testing. Now the previous two methods that we have seen, PT and MT, many times we categorize defects as surface, subsurface, and internal. So what previous methods, what we have seen, they are used for detecting surface and subsurface defects. Now, the next two methods, what we are going to see, that is radiography testing and ultrasonic testing, they are more importantly used for detecting internal defects. So what you see here is a simple picture which is appearing again, where I have explained the principles. We can talk here itself, where you have a radiation source, and suppose it's a weld, then all the radiations will be falling like this, as shown in the picture. And then you have a film on the other side. And then based on the materials, it will density and other properties, specific gravity and all, it will absorb certain amount of radiation. Now the absorption on this, and absorption with the reinforcement here, and absorption where you have a defect, they are going to be different. As you can see, where there is a defect, more radiation will fall on the film, and where there is no defect, radiation will get absorbed more, and less of it will fall on the film. And once having exposed this film with the radiation, then if I process this film like silver nitrate and silver bromide solutions, this darkening will take place, and that because of the more radiation coming in, this portion will be more darker as compared to the others. And in the radiograph, we see this as a porosity, which is a dark spot, or any other dark thing that we see, we tend to believe that it is a defect. That is because more radiation has passed through that defect, and it has interacted with the developing media and giving a darkness. Now, it's not so simple, because there are various other things which are to be seen here, which we'll see in the subsequent slides. But there could be two types of X-rays or radiations that we can use for radiography. One is the X-ray, other is the gamma ray. Both are not same. Both has got some advantages, and where to use what, we should be able to know that. Then you have something like image quality indicators. We'll see what it is. It is an image quality indicator. It is not a defect indicator. Many people think that if I am able to see 0.2 mm wire on the film, I am able to see the 0.2 mm defect also on the film. It is not like that. So it is strictly an image quality indicator. If you're able to see 0.2 mm thick wire, which the IQI is having, then that doesn't mean that you will be able to see 0.2 mm defect also. Then we'll see radiographic techniques also, some of the techniques which are used, and then go to the other parts. Now here we can detect all kinds of defects which are there in the welds, like even intention is not to see the surface corrosion, but if at all there is something, it can be detected. Then you have surface cracks or internal cracks, porosities, lack of fusion, and all these kind of defects, welding defects, can be detected by radiography method. Now in comparison to UT, this is more easy to detect three-dimensional defects in radiography, and two-dimensional defects are difficult to catch in radiography. Like very tight cracks, you may miss it in radiography, whereas you may not miss in ultrasonics. So, as I said, there is a X-ray. In X-ray, you are artificially producing X-rays in a cathode ray tube when you have a anode which is giving a high intensity and electrons, and which are suddenly losing their velocities by having a filament, and then that makes a generation of X-rays. And X-rays are used for up to thicknesses recommended for low thickness for higher sensitivity point of view. And for high thickness, you have other methods available, so you don't use X-rays. You will be using gamma radiography. We'll see this further how it is. We have X-rays and gamma rays. The gamma rays are naturally occurring radioactive sources, which will it keeps on radiating all the time. You have no control. Like today I have a say radium-192 source of some strength, say 20 curies. After some times, it is continuously radiating, whether you use or you don't use, it is radiating, and the strength keeps on reducing. Each source has got a half-life. We'll see what. And unlike that, you have an X-ray equipment where you generate X-rays. When you turn on the machines, these X-rays are generated. When you turn the machine off, the X-rays are not generated, and they are quite safe. Unlike gamma radiography, where even if there is nothing like on or off, you have an X-ray camera, gamma ray camera, you are exposed to the radiation if you don't take care. So this is the camera gamma ray what I am talking about. This is the camera what we say, and then it has got a cranking unit, a diving unit, and then it has got a tube where it has got an arrangement to push the source. When I do a cranking, the source from the camera goes out through the tube and it goes to the location where I place it to take a radiograph. And this is because of safety reason, because the operator can remotely operate this maybe from 22 feet or a little like that. And he's a bit safe. And once the exposure time is calculated based upon what material you are doing a radiography, he will again re-crank that and bring the source back into the camera. Then he will go and remove the other things and films and all for developing. So that is the arrangement. You have X-ray and gamma ray. For X-ray and gamma ray, anything what you need is the source, that is one. Then you require radiography films and screens. Then what we call as penetrometers or IQI, as I indicated in the previous slide, image quality indicator. IQI is image quality indicator. We also call it a penetrometer. Then you have LED numbers and arrows for indicating the various locations, defining this is my weld and the weld starts from here, and the LED numbers indicating what is the joint number and all that. You have a radiography room or where you're doing the processing, dark room and all that. Then you have a radiography viewing room. Again, it is with the subdued light so that you can do it properly. And then some safety to be followed when you're doing either X-ray or gamma radiography. For gamma radiography, we have generally using 3 radiation sources, that is natural isotopes, cobalt-60 or iridium-192, or recently, in the last few years, this selenium-75 has come because there was, for lower thicknesses, sensitivity issues were there, where iridium-192 was being used, but not giving a sensitivity. So people, instead of opting for X-ray, you have in between some other option available by using selenium-75. Selenium-75 gives you sensitivity somewhere better than iridium-92 source and little, I would say, worse than X-ray. So here the geometrical parameters are important. The distance of source to the object and distance of this film from the object. It has to be as close to the object as possible, because the geometric conditions will be such that we don't want to have a divergence of the radiation, control the divergence as much as possible. So if I have a very long film like this, so my radiation from here is falling here, going towards the length of the film, where actually my thickness is only this much. So if this much is appearing like such a long thing, that means I have divergence which is very, very high, and I will not be able to get a good image. What we call this controlling factor is a geometric unsharpness, which is controlled by this formula, which we need not worry about these formulas and all that. Outcome will be known if we have a good film. That means all the parameters are under control. Now, just to show this cobalt-60 has it is showing 53, but it's not 53. It's 5.3 years is the half-life, and iridium-192 is 74 days half-life, and selenium-75 is 120 days half-life. Half-life is, suppose today I have 20 curie source here. My 20 curie, after 120 days, the selenium will become 10 curies. My 20 curies cobalt, after 5.3 years, will become 10 curies. My 20 curies iridium-192, after 74 days, it will become 10 curies. That is half-life. So this, as we can see, half-life of this is better than iridium. So even the sensitivity is better than iridium. So this is now the option which we go for when you are doing an X-ray of 10 mm and below. Up to 5 to 10 mm, this is the best source to carry out the X-ray. Now, some difference between X-ray and gamma ray. Again, I will not go into too much detail because we know X-ray we can control. We are not totally exposed to the radiation all the time. And where there is gamma rays, you are exposed all the time. It is giving a high contrast and good definition X-ray, whereas gamma radiography gives you slightly inferior sensitivity. Whereas the source focal spot is the one which is the governing factor. The focal spot is smaller. The smaller the focal spot, the better is the X-ray and sensitivity that you are going to get. So X-ray focal spot is small compared to the gamma radiography. That's why it is giving a good contrast and the other things. Other factor is the film. The type of film that you are going to use is going to make a difference about the final sensitivity that I am going to get. If there are issues in getting a required sensitivity for the materials which are having less thickness, then it is advised to go for D4 or D5 films. D2 will not be so practical because exposure times becomes very, very high. But D4, definitely you will have to go for D4 film. If you have to do gamma radiography of say 3 mm, 4 mm, 5 mm stainless steel or cupronickel or aluminum, things like that, then you have to go for D4 films with selenium 75 source. And if you still don't get the required sensitivity, you have no choice but to go for X-ray. Coming to a bit about image quality indicators, there are two types. For welds, generally widely used is the wire type, which you'll see. And for castings, the people do use a hole type pentameter also. Now, don't go by these images. These are only to identify different material, different notches are there. So consider it only on this. So hole type, you have some thickness of the pentameter based on the designation given here. It is almost 12 thou or 15 thou will be there. That means 12,000 of an inch or 15,000 of an inch. That is the thickness of the pentameter. And over that you have either 1T, that is 1 thickness diameter hole, 2 thickness diameter hole, and 4 thickness diameter hole. They're all arranged in this fashion only. The one is in the smallest hole is in between. Then the next one is towards the end, and the bigger one is towards this end. Whereas in wire type, you have now ASTM wire type, you have 6 wires and there are 4 sets like this. Set A, set B, set C, and set D. So, and each set will have different range of thickness of wires. So for wire welds, we generally use this ASTM pentameters to check the sensitivity of the film. The IQA is only used to check the quality of the radiograph, not the size of the. How to check that is sensitivity for wire type is very simple formula given. Diameter of the smallest wire that I am able to see in the radiograph. Smallest wire is, suppose out of this, I am able to see this wire. So this is the smallest wire I can see. I'm not able to see this. So this is the smallest wire I am able to see. So that smallest wire, and what is the thickness of my job? So suppose I am able to see 0.2 mm small wire on a 10 mm thick job into 100. So I have 10. So 2% sensitivity I will get. So generally, ideally 2% is the acceptable norm. But now the codes have slightly become more practical where, in lower thickness, 2% is difficult to achieve. In a higher thickness, 2% is easy to achieve. So they have made a table where it doesn't talk about 2% or 4%. It says that this is the thickness, this should be the wire visible straight away. So for lesser thickness, they are asking for a better, it could be 1.8% also sensitivity. But for higher thicknesses, it is slightly different. Oh, sorry, for lower thickness, they accept up to 3.5% sensitivity also because it is difficult to achieve. And for higher thickness, you go for even 1.5 and 1.8. For hole types, this is a formula used 100 by x under root th by 2. Thickness of the pentameter and hole diameter, and this is the job thickness. Coming to the techniques, some of the techniques we'll just see what is when you're doing an X-ray radiograph, either X-ray or gamma ray. When I use X-ray is the term generally used, but technically when I say X-ray, it should be X-ray means the X-ray is produced in a CRT, that X-ray tube. But I am generally using the term X-ray to define X-ray as well as gamma ray. So we have one simple technique where if you're using a plate, if you're carrying out a X-ray or radiography on a plate, like a hull plate, which is long, and you have to do X-ray of that. Then you have to use the technique which is called single wall, single image. Single wall means the radiation is penetrating through one wall, and what you're getting is a one image. So that's why we call it single wall, single image. And this is the kind of thing that you will see on the radiograph. This is the IQI, what I'm saying, the image quality indicator. You can see maybe this is an X-ray as I appear, this is an X-ray, and you are able to see all the 6 wires or 7 wires which are available. So based on what is the thickness of the last wire and what is my job thickness, I can calculate what is the sensitivity that I've got. And with respect to the procedure qualification, the code for others, there are different ways how to qualify a procedure. But for radiography, it is very simple. There are so many varying factors which we have seen. But if I have produced a radiograph which is giving me a good density and sensitivity, is giving me an indication that the procedure has been correctly followed. So what I need to get is a good density and a sensitivity. So this is again a single wall, single image. Now here you have a double wall single image, which is generally done on pipes which are of a diameter from say 3 inches to 12 inches, 14 inches. You carry out this double wall single image. The radiation is penetrating through 2 thicknesses. That is why it is called double wall. And what you are getting is a single image. So it is a double wall single image technique. Then another technique is what is called as a panoramic technique. Here what you do is this is used for big size pipes, like you have a 20-inch pipe or even bigger size 64-inch pipe or larger diameters also, where you place the source in the center of the pipe where you have a weld, and then you place the film outside all around, and with a single exposure the entire circumference of the weld is getting exposed. So that is called a panoramic technique. Then you have a double wall double image. You must have seen, some of you must have seen elliptical shot. We call it as elliptical because the weld appears like an ellipse. So this technique is applied only on pipes which are less than 3-inch diameters. 3 inches, 2.5 inch, 2 inch, 1.5 inch, even 1/2 inch and 3/4 inch also. Bit difficult. People go for other method, but yes, it is possible. You have to, what you do is you have to keep the source such that you have the image of both these welds. You can see the bottom weld and the top weld, both are there, but the edges are not clear or having a good contrast. So what we do is you take one shot and then you rotate this source to 90 degrees and take one more shot. So when you rotate 90 degrees, you get this image also coming in between and you are able to see the entire weld. So in this case, two images will give you the entire full radiograph of the weld. Whereas in other cases, depending upon the diameter and thickness, you may require 3 films, 4 films, 10 films. Now in the radiograph, there should not be variation in the density. What the code permits is minus 15% and plus 30%. The variation should not be more than that. And with respect to what? With respect to the density that you have achieved in the designated wire that you are required to see. Suppose I am required to see a 0.2 mm wire, then across the wire from the base metal to the weld, I check the density on the weld, and whatever density I get, that density should not vary in the entire film from minus 15 to plus 30%. And if there is a variation, you have to reject the radiograph, or next time you do, if there is a problem in the technique, you have to put 2 pentameters, giving me a different proper evaluation. And for panoramic technique, no need to place IQI in each film. What you need to do is you divide the segment 120 degrees, and each 120 degree segment, there has to be a 1 pentameter, as this is what the code says. Now, before you do the interpretation of the film, what is required to be seen is the First is the film, whether it has been taken properly, X-ray has been taken properly or not. It is not having anything which is objectionable. And then once you find it is okay, then you have to see the area of interest, whether that is having a proper defect-free image or not. Now there could be because of processing, or there could be some defects introduced because of processing, which you have to be careful. It should not be on the weld area of interest, should not have these kind of welds like watermarks or some bending of the film or some excess darkness because of processing, all these things. Fog, light leakage. Fog is light leakage. White light has leaked and it has become very dark on certain areas. So these things you have to see first. Also, your density is okay. Generally, density, since we're talking about what the code says is, I'm talking about the same code again, ASME. For gamma radiography, density required is 2 to 4. For gamma radiography, you can accept minimum 2 and maximum 4 as a density. Whereas for X-ray, you can accept 1.8 to 4. X-ray, you can go slightly on the lower side also. It gives better sensitivity. So 1.8 to 4 is acceptable. Then the contrast is okay or not, density is, sensitivity, everything is okay. Then you start the interpretation for looking for the defects. So there are two things what's to be seen before you actually start evaluating a radiograph. One is whether it is not having any process mark or spurious indications which are masking my defect area of interest. Other thing is that proper exposure times and density sensitivity is achieved, which is required to be achieved for that particular technique and the thickness of the job that is being radiographed. Once that is meeting the requirement, then you can evaluate the radiograph as per the code that you're following. Now, important things to remember in this is your examination to be performed as per a written procedure. This goes without saying for any technique. We'll talk this in the end also. It requires a written procedure approved by a level 3, which should be followed for doing any NDT. So previous code for radiography section 5 was not giving a mandatory requirement for a procedure for radiography. It was saying that when the density and sensitivity is okay, it assumes that the procedure has been correctly followed. But now in the new revision, they have indicated for radiography also, the written procedure should be there, which would talk about minimum material type and thickness range that you're seeing. If the procedure doesn't talk about thickness range, I would be using a gamma ray for 100 mm thickness also, which is not permitted. Gamma ray generally is from 10 mm to 65 mm is the right range where you can do a gamma radiography. If it is with iridium 192, if it is cobalt, you can go up to 5 inches also. So like that, if ranges is not mentioned, thickness range, you are not able to decide whether my procedure is going to work well or not. Then whether you are using X-ray or gamma radiography. Source to object distance, distance from source to the film, size of the source, sensitivity and density of the radiograph that is required, the film brand and designation, that means with NDT 65 ultrafine film or which type of film is used, and the screens which are used to protect backscatter and other things. And other thing not mentioned here, but it is assumed that it is required is acceptance standard. We know what is the acceptance standard. Then only you can do a proper interpretation. So that was about radiography. I think brief essential things have been talked about. And if anything anybody thinks is missing, maybe you can have a note and we can discuss at the end. Next important method that we have for checking internal defects is ultrasonic testing. Now what we are talking about is only a conventional ultrasonic testing method. And now many of you must be knowing that there are advanced techniques which are phased array, UT, and TOFD, that is time of flight diffraction technique, where high techniques are available, which will give you much better results compared to what we are getting in a conventional method. At the same time, they are very, very costly, and but they are being used widely for critical jobs. So here we'll see what are the principles of UT, what are the different types of probes. And for each type of what I've covered is at least we should know when we are witnessing UT being done by somebody on your job, we should know how they are doing the calibrations and all that. These are basic things which we should understand. And just a brief about how the weld testing is done. Again, there are so many things involved in that, but I'll give an idea of how generally it is done, so that you have some idea about that. Then again, advantages and limitations that we have in UT. So ultrasonic testing. Ultrasound is the sound that we cannot hear. Audible range. It is much beyond the audible range. Our audible range is generally up to 20,000 kilohertz, like 20,000 kilohertz. And the testing that we do using ultrasonic is generally from 1 megahertz to 5 megahertz, which is much beyond the audible range. We do go up 0.5 megahertz also for certain applications like castings, which are coarse grain structure, where you use for lower frequencies. But generally in industrial application, we have 1 megahertz to 5 megahertz probes which are used. Now we know that there is a normal beam probe and shear wave probe. We all know about these terminologies, and in shear wave or angle beam probes. Now angles we have in conventional methods, angles generally that is used is 45 degrees, 60 degrees, and 70 degrees angle probes. A normal beam probe is the standard probe, which we call it also a 0 degree probe, which is going perpendicular to the surface and coming back. Now, to understand what is 45 degrees, 60 degrees, and 70 degree, how it is generated, this small sketch, what is shown here, I'll explain, and then you'll have an idea how the angle probes are generated. Angle beam is generated. Now, if you see here, there is a longitudinal wave at an angle. So all red is my longitudinal wave, and blue is my shear wave. Now here I have an interface. Interface I've taken is say plastic and steel. Okay, and now in that interface I have introduced a longitudinal wave at an angle. Now at the interface, it is going to split into a refracted longitudinal wave and a refracted shear wave. And there it will be a reflected longitudinal wave and a reflected shear wave. We are not worried about this. Now we have two waves in the material. We cannot do any testing because there are two waves and each is having a different velocity. The longitudinal wave is having about, in steel we are talking about 6,000 meter per second is the speed of longitudinal wave in steel, whereas shear wave there is about 3,200 meter per second. So with these two different velocities waves, they will be going in and coming back, and you're not able to interpret what's happening, like which wave is come back and what is my defect indication, what is my actual wave which has come back transmission. Now what we do is you increase this angle further and try to remove this wave from the surface. So as I increase this angle, at one time I will have this wave parallel to this surface. So no more introduced in the material. So that is the time I have only shear wave in the material. That is, I can have either 45 degrees, I can have 60 degrees, I can have 70 degrees, only shear wave. I have excluded this from the surface. And then I can vary this angle to get 60, 70 or 45. So that is how the waves are generated, angle beam probes, what we have. And this is the law, which is called Snell's law. When we have this, the sine of alpha upon sine beta will give you the velocity of the material in plastic and the velocity of the material in steel. Again, coming back to the normal beam probes, there could be a single crystal probe, which is a single crystal is acting as a transmitter as well as a receiver, or there could be a dual crystal probe, which we call it a TR probe, where one element is transmitting and the same one element is receiving, which is there in the same probe. Okay, here single crystal is acting as a transmitter as well as receiver, whereas here there are two crystals within the probe with a barrier which you're not able to see here. There is a barrier here and there are two connections you can see, one for the transmitter and receiver. Here there is only one. So that is a difference between a TR probe and a normal conventional probe, straight beam probe. The advantage here is that this gives a high resolution and a better for checking some certain thicknesses and where the dead zone is, near field effects are less. But the calibration we need to understand. In the industry, I have seen many people wrongly do the calibration for TR probe. We need to understand this so that we don't make a mistake. Angle probes, this is how, if it is 45 degrees, the ray will come out at 45 degrees, 60 degrees will come at 60 degrees, and like that. Straight beam goes straight at 0 degrees, hit the indication, come back. Here, if the defect is large, the entire rays will come back and you will get a very good indication. If the defect is small, some of the rays will come back from the defect, some will hit the back surface and come back, and your indication could be varying in length with the echo height. So in a normal beam probe, this is what is, we call it as a near field effect, a near zone or a dead zone, where you are not able to pick up any indication, or it is not used to do any kind of testing because it is a lot of electrical disturbances within this region. So what the testing is done is generally in the far field effect from here to here. So this near field is reduced in case of using a TR probe. So this I explained how the waves interact with the defect. Now how to do the calibration using a single, this is not a TR probe, a single crystal probe. This block that you see here is called a V1 block. It's a standard block having standard dimensions. This thickness is 25 mm and this is 100 mm. We are talking about only 25 mm. So if I keep a probe here and it goes straight beam probe 25 mm and comes back, on the screen I'm seeing how many peaks I'm seeing. I'm seeing 4 peaks. 1, 2, 3, and fourth one. So fourth peak means I have a 25 mm, 50 mm, 75 mm, and 100 mm. So if I have 4 peaks within my full range, I am having 25 into 4, that is 100 mm range. My range is 100 mm. So if I want to have a range of 50 mm using the same thick block, then what I need to do is the second echo, this is 25 and this is 50. This 50, I will turn the knobs, delay knob, and bring it on this full range. So my range entire will become 0 to 50. This is how the calibration done using a single crystal normal probe. Now, if you have a dual crystal, this is how dual crystal probe is having the construction. Like you have 2 crystals here, one acts as a transmitter, other is acting as a receiver. And there is a barrier inside so that they don't crosstalk between each other. And then the rays goes like this. As you can see here, it doesn't come directly perpendicular as in case of single crystal. It is having some sort of angle. So in here we were using, this is called multiple echoes. We are using multiple echoes for doing a calibration. So for 100 mm range, we have set 4 multiple echoes and got a 100 mm range. The same thing we cannot do here because multiple echoes means there would be error because it is going at an angle, not going straight, it is slightly at an angle. So this will result in an error. So what we need to do to calibrate this TR probe is, suppose I want to have a range of say 10 mm. So I have to always use 2 thicknesses. So in this case, I am using a 3 mm, this is a step edge block. Each step is 1 mm say. So I'm using a 3 mm here and 6 mm here. So I keep 3 mm and see on my screen whether I'm getting 3 mm reading. Then I put the probe on 6 mm and see that I am getting 6 mm. You may require adjustments once or twice to make sure that 3 mm is showing me 3 and 6 is showing me 6. When once this happens, then you're having a range of proper 6 mm or up to 10 mm. If you want to have a range of 20 mm, say 50 mm, then you have to have intermediate 2 thicknesses and do the calibration using 2 thicknesses. If you do calibration using say multiple echoes in this case, then your thickness variation would be there. For critical jobs, I've seen people doing this where pressure vessel in service inspection they are doing, they're checking by multiple echoes and the tolerances are so less, and if your error itself is quite high, then instead of accepting a vessel for another 20 years, maybe you'll be rejecting after 10 years, saying that there is a lot of loss of thickness, so it is not acceptable. So we have to be careful about these things. Now we see how we do a calibration of a range setting of a angle beam probe. Now angle beam probe, there you are having a V1 block, what we had seen earlier. This is a V1 block. Here you have a V2 block, a smaller block which can be carried to the field, which is called a V2 block, which is having dual curvature. It is having a curvature here and it is having a curvature here. This curvature is what is shown here is a 50 mm and this curvature is 75 mm. So if my probe I'm keeping facing this curvature, then my first echo will come from 50 and the second echo will travel 75, but it will not get picked up because probe is facing in the other direction. So 75 and travel again 50. The second peak will come at 50 plus 75. That is 125. Third will come at, again, you keep on adding 75 each time. This is how the multiple peaks will be coming from an angle beam probe, which is having a double curvature. This curvature could be different, like, I can have a 25 curvature and a 50 curvature, or 50 curvature and a 75 curvature. So I should know how the beam is traveling. And based on that, I can use a multiple echo to have a fixed range in my equipment using angle beam probe. Like here, there is a 25 mm and 50 mm. No, 25 mm and 75 mm. So here it is explained also, like, first peak is coming from 25, second comes after 75, that is 100, and after each multiple of 75, next will come at 175, then 225, like that. Now for weld scanning, now we have already seen the thickness checking. For thickness checking, what you require to do is use only normal beam probe. Even for lamination testing, you have to use only normal beam probe. And how we calibrate, we have seen. For lamination checking, sometimes they calibrate on the job itself by taking a back reflection from the plate. But if you have to do a weld scanning, then you have to plot what is called as a DAC, distance amplitude correction. Distance amplitude correction curve has to be plotted, and how it is plotted is by having a artificial defect on a plate, drilled holes. This time blocks are available, or we can prepare also. The UT operators, they all have these blocks with them. You can have a single hole block, or you can have multiple holes. Here we are seeing 3 holes. One is at T by 3, T by 4 thickness. Other is at half thickness. Other is 3 T by 4 thickness. So what we do is we have to probe position. This is probe position 1, 2, 3, and then it has gone like this. So 1, it is hitting the first hole. Second, it is hitting a middle hole. Third, it is hitting the bottom hole. And fourth, it is hitting the bottom hole after a bounce. So here the first one, we have to make sure that the indication which I got, first one, I have to adjust the probe such that I get a peak. Where I get a peak, I will mark that point as point number 1, and then go to this place. Again, when I pick up this indication, I'll try to maximize, and I mark this point as 2, where I get this maximum indication. Then I go to 3, and I mark this as maximum 3, and then 4, which is shown very low here, and then join these peaks, and this dotted line is my DAC, what is called as a distance amplitude correction curve. What is the implication of this is that this is the defect here, which is very closer to the probe. Okay, and it is giving me this much amplitude. Now, if the same defect I'm picking at a different beam path, the probe is somewhere else, but the size of the hole is the same. Because I have traveled inside so much that there are losses due to absorption and scattering, which is giving me a less indication. So what I get here, peak, after traveling so much distance, and what I get here as a peak, after traveling only this much distance, my defect size is the same. So that is why I prepare a distance amplitude correction curve. It is a correction, like, I correct this amplitude to this, whatever inside I travel within the material, to say that this height and this height from defect point of view, they are same. Okay. So once I have this DAC, then I will actually set a range and do scanning on the job, on the weld. I'll see in the subsequent slides. And then you scan between the peaks. You find a peak in between this, then you know that to what percentage of this height I'm getting a peak. So we have to evaluate. And if it crosses this peak, I know that my defect is bigger than what I have calibrated for. And definitely it is more than 2 millimeter size or something like that. So that is why you need to have a distant amplitude correction curve for weld scanning. So these are some of the trigonometric simple formula that we use for estimating or calculating the distances. You have surface skip distance. Skip distance is what we call it as when it is hitting my probe, when it is hitting the root. Say this one, this probe, when it is hitting the root means the back surface of the material. So when this hits and it bounces and goes back to the surface, this is forming a full V. So I call it a V path, full V path. So this is a full V path. The full V path where I get the indication, I call it on the top surface as a skip distance. So this is my total skip distance. So you have to scan a weld. I need to go a little beyond because I have a reinforcement also. So I need to do 1.5 skip scanning to do scanning on the weld. 1.5 skip distance I have to scan. So 1.5 skip I can calculate using this formula. Skip distance 2t tan theta. If my probe is 45, straightaway I get twice the thickness. If it is 25 mm, I get 50 mm, and a little beyond that half. That's 50, 20, 20, 40, and 10, 50 mm. I can set the range and then do the scanning like this. Again, I have taken this picture to have explained parallelly. So once having got the DAC, depending upon what is the thickness, I will set the range using a V2 block. Now in this case, suppose this is 20 mm. If I set a range of 150 mm, will give me a good range to cover my top surface and the bottom surface. And I will set the range 125 mm using that V2 block. Once that is set, now I have to do only a scanning. My scan here, if I put the probe here, I get the indication from the root. And if I put the probe here, I get the indication after a bounce and I reach the surface. It is like this. So if I scan between this, I'm scanning the root as well as the top surface. That means I'm scanning the entire volume of the weld. Now the good practice is if it is a butt weld which is accessible from both the sides, you have to do the scanning from both the sides. Although with one side I'm able to cover the entire weld, but since the surface is available, we do not know the orientation of the defect and all that. So it is better to check from the other surface also in the similar fashion. Now, what are the other things that are to be looked into? This is once I have done this, plotted this DAC, I note down what is the amplitude shown in my UT machine. Suppose it is 38 decibels. I note that as a 38 decibels. Scanning has to be always done 6 decibels more than, that is double sensitivity we call it. But before that, you will realize that I am doing calibration on this job, which is a machined plate having a machined holes, and the surface is really very good. Whereas when I do testing on the job, my surface may not be as good as this. The surface will be must be rough and having sometimes rusted also, and will not be able to transmit as better as I get a transmission here. So there is a correction factor. So what we call it as a transfer correction. So when I transfer the probe from this surface to this surface, how much is the difference in the amplitude I'm getting? That is called as transfer correction. So that I have to note and add into my, after plotting this DAC, whatever 2 dB or 3 dB I'm getting extra, I have to add this to take care of the difference in the transfer correction, difference in the surfaces that we are having. This is a smooth surface, this is a rough surface. Again, the calculations of surface distance, as I said, sine theta into sound beam path. Sound beam path is what the sound travels inside the beam before hitting a defect. what is the total travel, that is, we call it as a sound beam. And then what is the depth also we can find out using cos theta and sound beam path. Again, depth is from top surface, how deep it is. If it is a direct hit, if it is after a bounce, then you have to remove one thickness from that. So these are some of the patterns scanning. What we need to do is cover the entire thing. So we have to scan from half skip. Half skip is where I get an indication from the root. To full skip is where I get an indication from the surface, and go a little beyond that to cover the reinforcement. I need to cover the reinforcement also. Different types of calibration blocks. As I said, this is a V1 block, this is V2 block. These are step wedge blocks of different thicknesses, steps. And these are again circular different type of blocks for calibration. Now, what are the advantages of ultrasonic testing? You can check internal flaws. I would say people are more confident in radiography because they are able to see the film, and they have less confidence on ultrasonic testing because they think that it is more dependent on the skill of the operator, and we are not able to monitor. We do not know how much skilled he is, and the confidence level goes down. But from the technique point of view, the radiography, as I said, is giving you defects which are not so critical, but you are able to see well. But UT is giving you the defects which are very, very critical from the service point of view, like lack of sidewall fusion, which is very critical. You will not detect in radiography, but easily you can detect in ultrasonic testing. Even tight cracks, which you may miss out in radiography, you will be able to pick up in ultrasonic test. So always give more, I would say, confidence reliance on ultrasonic testing with respect to radiography. Only thing is what to be controlled, we'll see later, so that we have more confidence. So this is best suited for two-dimensional defects. As I said, planar defects like cracks, lack of penetration, lack of sidewall fusion. These are best picked up by ultrasonic testing. Material thicknesses from 10 mm onwards, it can detect very easily. And now the advanced techniques and probes are available where you can go lesser than 10 also. In fact, AWS D1.1 code, which is for structural welding, they allow from 8 mm to 200 mm UT to be done as per that code. To 8 mm is the minimum thickness they allow. Then this is the best method to detect laminations. We know we use very widely the technique is used to detect laminations. There are various codes available also as ASTM 435 and 578, which gives the ways how to do lamination check and what is the extent of lamination that can be accepted. Widely used for thickness measurement. That is the what Mr. Jain had mentioned in the beginning. You have thickness measurements in the ship hull structures, and where you have so many service providers approved by the class who do regularly thickness checking and monitoring the diminution of the material. Equipment is very portable, easy to carry, no safety hazards. Limitations which are still to a large extent are not really limitations now, because we have equipments which can now give you a record. Whatever DAC is made, I can store that DAC for a particular job, and I can reproduce again if I'm doing the same job again. So these things are available in the modern UT machines. Heavy dependence on the skill. Yes, it is depending on the skill of the operator, and we have to be very careful to see that the person who is employed to carry out the test is really a competent person. And I've seen in the industry, people rely on the certificate and think that the person is competent. I would suggest that some sort of test has to be done for each kind of job. The client should test the competency and before allowing him to do the job. Less sensitive for three-dimensional defects, like compared to RT, that is, porosities and all can be easily picked up in radiography, whereas some porosities, clusters and small, which sometimes get into the noise level of the instrument and may not be able to pick up. Transverse defect difficult Defects lying parallel to the surface, again, like empty, the defect has to be perpendicular to the sound beam to have the best amplitude. If it is parallel, you will not be able to pick up. Applicable codes for this, you have 317 is for checking the equipment characteristics, actually, whether the equipment is okay or not, the vertical linearity and the horizontal linearity. We can check using this 317. I've added this one more code for lamination checking. Normally we have this ASTM 435 and 578. In 578, there are level A, level B, level C. Based on the criticality, you have these levels. We can decide on generally used is 578 level B. Then you have section 5, article 4 and 5. The article 4 is for the welds and article 5 is for the materials. UT of welds, guidelines are given in 4. UT of materials, it is given in 5. Acceptance standard is given in section 8, division 1, appendix 12 for UT. Then you have guidelines given in ASTM 388 for testing forgings. Then you have for walls, as I was telling earlier, SME B16.34, appendix 1, 2, 3, and 4, each is giving acceptance norm for PT, MT, UT, and RT. So this is not clear. That's why I have added this what points to be considered important. Okay. Oh, that is missed out in this. I don't see. Yeah, it is there. So here, what is important is what is the thickness, what is the configuration of my joint? Like, weld could be a T joint or a corner joint or TKY type of joint. What is the weld configuration is important. For each configuration, you need to have a proper scan plan available to ensure from where I'm keeping the probe and from where I'm getting the indication whether all those things are proper or not. Type of instrument, whether the instrument is able to pick up and in workable condition. Search unit type, that is probe, 60 degrees, 70 degree, which I'm using. Speed of scanning, the code allows up to 150 mm per second, 6 inch per second. You should not go beyond that, but generally we do follow much below this. Technique, whether you are using straight beam or angle beam. Calibration block and sensitivity. Again, for guidance, if you want, you can have a look on ASTM ASME section 5, article 4, which gives you a table, I think T434, which mentions about different thickness, what should be the size of the hole that you can use for picking up your sensitivity. Direction and extent of scanning. Sometimes there are limitations with respect to extent of scanning, which should be reported in the report that you get, so that you know where things were not able to detect and what actions you have to take. You should be aware of that. Methods of discriminating geometric from flaw indications. Now in ultrasonics, many times you get the geometric indications. And now, unlike PT, where it is very easy to make out what indication is relevant and non-relevant, in UT, unless the operator is having a skill, he will not be able to find out whether it is a real defect indication or it is an indication coming from a surface because of a spatter on the surface or a small undercut on the surface. There could be these kind of indications coming in where one should know how to differentiate a real indication from a geometric indication. You have to actually plot 1:1 scale the weld and plot the beam, how much it has traveled from where you got the indication, to decide whether it could be real or it could be geometric. The type of couplant. For couplant, it is important that we use the same couplant for calibration and the same couplant on the job. If there is a difference in the couplant, again, during calibration on the job, the transmission characteristics would be different and your results will be having this error. Also, the couplant should not be detrimental to the surface where you're using UT, particularly for stainless steels. Again, the requirements are same. The couplant used should not have more than 250 ppm of sulfur and chlorides and fluorides and all. Surface conditions and transfer correction I explained because the surface of the calibration block is different and the job is different. So we have to have a correction of that. Again, this is again very important temperature variation where people try to ignore and they are not aware of this, but things may vary. The results may vary if you don't give importance to this. What is that? Temperature variation between the calibration block and the scanning surfaces should not be more than plus minus 14 degrees centigrade. Now you see, calibration generally is done in an AC room where the temperature could be maybe 20, 24, somewhere around that. And testing in, say, summer is done outside where the temperature could be 30, 35, or it could be 40, like that. So you see the difference is going much beyond that, which is permitted by the code. It could result in variations and errors in your system, which you should be very, very careful. So in such cases, we have to advise the operator to do the calibration on the field where he is going to scan the surface so that the temperature variation is not much. The UT operator's performance qualification. This is important because as it is seen that it requires high skill, the operator's qualification becomes an important factor. And I would say the operator, the machine, and the method are important for all the NDT techniques that we have seen, which we will see a little bit more about the qualification process. Now, with this, I think I've covered all the 4 techniques, whatever important things I wanted to, with the basic principles, giving you just time to refresh on. Now, what the code talks about is procedure validation. Now, this is very widely used in the industry, and I would suggest that in the marine industry also people are aware and they adopt these kind of good practices which are available to see that the job is performed in an appropriate manner. The code says in the para that I have mentioned here, T150 of Article 1, which says that procedures should be validated. That means I have documented a procedure which is approved by a NDT level 3, which is supposed to work. Now, when I do the job first time, I make sure using the parameters which are given in the procedure are really working and they are able to pick up the defect which is supposed to be picked up. That is a procedure validation. Means demonstration of a procedure that it is working well. Like you are qualifying a welding procedure. The purpose is the same, that field, when you're doing a production welding, it is meeting your requirement. That is why you are doing a procedure qualification for the welding. Same way for NDT also, there is a procedure qualification which needs to be done at one time. And subsequently, you have to make sure each time you follow the same procedure. There are essential variables which I mentioned in the one of the slides, section 5 requirements, essential, non-essential, which if we are varying essential requirement, then you have to demonstrate the procedure once again. So what is validation is you are seeing the competency of the person who is carrying out the test. Automatically he gets approved. Then the machine which is used for doing the test is checked and accepted. And the procedure which is already supposed to be previously approved before they actually do the qualification test is a proper procedure which is approved by a competent level 3. Don't go by only the certificates. Even level 3 certificate also, I would say, I can give you an example in my previous company where we used to regularly in shortage of level 3s, and we were regularly conducting interviews. Out of 10 interviews we conduct for a level 3, except only 1 will pass. Like they have level 3. Nowadays what's happening is the college students, as soon as they pass, they know the importance of this certification. They will take 2 months off, study, and sit in the exam, get the certificate, but they don't have any knowledge about practical exposure and things like that. So they are not able to perform well in the field. So this is the importance, I would say, that I have seen it also practically. Out of 10 level 3s which we used to interview, our requirement was for every project to have a level 3. So out of 10, we used to get sometimes 1, and sometimes we used to compromise. Okay, he's somewhat good. Let him come, and we will take care of the rest of the things where he's lacking. Okay. Now, lastly, before I end, I had mentioned that I would also mention a few things about the certification schemes which are available. And what is widely used in, many of you must be having certifications level 2. This is the most, I would say, not correctly interpreted scheme and certification widely available not only in India, in elsewhere also in UAE, which is misused, is the one which is shown in the bottom, ASNT, SNTTC 1. If you have a ASNT level 2, many of us in India are having, and it is not meeting the code requirement. What ASNT says is that in this document SNTTC 1A, that they have given the norms of guidance for training, how many hours of training they should undergo, and what other things. Everything is detailed in this, and responsibility of level 1, level 2, level 3, everything is defined. It says that the employer has to certify level 1 and level 2. Employers, it has to be as per employer's written practice. Anybody having a level 3, what's happening in the industry is I have a level 3, I open a training institute, I start issuing certificates of level 2, where I do not know what competency and what checks have been made to ensure that when they go to work with the employer, whether they are meeting the employer's requirement or not, is nobody has assessed that. So that is why this this SNTTC 1A is a very good document. If it is used appropriately, judiciously, it is a good document. But because it is giving a lot of leeway on the manufacturers and all, it is misused by everyone. And even the end users are not aware that this kind of certification is really not valid. In fact, in November 2018, Materials Evaluation is a magazine of a periodical of ASNT. The ASNT's technical manager has given a 1.5-page article that these kind of certificates are not at all a valid certificate, because the ASNT doesn't issue level 2 certificate. ASNT issues level 2 means what is issued by a Columbia. ASNT is situated in Columbia, Ohio. They only issue, that is a level 2. Anybody else issuing certificate is not a level 2. So it has to be done by a written practice of a company. Now, ISO 9712 is now the most widely recognized internationally. It's not region-based. Earlier, it was region-based, like, in UK and some parts of Europe, they will have BINDT. BINDT is British Institute of Non-Destructive Testing. And they used to give PCN level 2, level 3 and all that, PCN personal certification norm. And then there was also EN 473, which was for European norms. EN 473 was again a certification, which was good. But now, after ISO has come, EN has become wide. So the best certification now available is ISO 9712, level 1, 2. Level 1 is not important, level 2 and level 3. Why it is so important is because it is a central certification scheme. It is not an individual certification scheme like any individual level 3 can issue a level 2 certificate. It's not individual based. It is central certification scheme. Only certain accreditation bodies are allowed to train and certify people, not everybody. So even if I am level 3, I am a level 3 in ISO 9712, but I cannot train and certify anybody for level 2. So moreover, this is a sector based. So ISO 9712 level 2 for welds. So welds is separate, forgings it is separate, castings it is separate, things like that. So it is more practical and more competency based, I would say. Once you have a level 2 9712, you don't doubt his competency. You know that he has undergone all the process for welds and he is be able to do a proper job for testing of the welds. Whereas ASNT level 2 is ASNT level 2. So whether welds or castings or forging or TKY joints, everything, he is an all-rounder for everything, but he may not be really competent to do many of the jobs. ISNT is another certification scheme, the Indian Society of NDT, where till recently their certification in India was very much accepted and recognized because they were doing a proper, somewhat similar to 9712 certification product base, and very rigorously they used to impart training to the people and then issue the certificate. Now, recently, because of lockdown, we didn't have meetings for last 2-3 months. We'll be having now tomorrow. We have a online meeting, and I think they have got the accreditation for 17024 for certification of level 2 people, and which is now level 2 certificate or level 3 certificate issued by ISNT. Very soon, they would be equivalent to 9712. So that is the certification scheme we should be accepting. The last preferred is, I would say, the most widely used is the last preferred certification scheme that you can have, because it's not properly utilized. Now, to have, if you want to use this SNTTC 1A level 2, what I would suggest is not to totally reject the people. They are also trained and they have undergone some knowledge and they do have some knowledge and competency. But whatever gap you see here and 9712, that gap should be identified and bridged. Then you can say that my person is having competency equivalent of that. For that matter, I would suggest that trade test to be conducted. Anybody utilizing, suppose I have to utilize level 2 9712 not available, but option I have got is SNTC 1A level 2 available. Okay, I conduct a trade test. I know for what purpose I'm going to use him. Then the most critical job that I'm going to suppose in my works I will tell him to do a test. And if he passes that test, I call it a trade test. And then I'm sure that yes, he has a competency and he can be utilized. So with this, I think some awareness to the certification scheme I have given. And I would once again thank Institute of Marine Engineers, all the senior committee members for giving me this opportunity to present share my experience on behalf of ISNT. And I hope whatever we discussed is somehow useful to the marine engineers, and it would have upgraded your knowledge, refreshed your knowledge, and also highlighted for each method. I have one slide which is very, very important, where important things should be under control, which we should always be looking into that. Thanks once again, and if any questions are there, we can have questions now.
So thank you so much, Mr. Sharma. It was an amazing session, and I'm sure many of the doubts of the candidates and participants and apprehension may have been resolved. I, for one, have learned a lot from today's session. I mean, after so many years in marine engineering, I think so many things which were in a shadow area are almost clear now. So thank you so much. It was really enlightening. And I'm sure that people who have any more queries and which they come to us, we can assure them that we will answer all the queries by email if you are not able to do it in the time allocated, because we can't have an extended question answer session because this topic is heavy. So we have already done almost a 2-hour session. So I would say that we will do a brief 5-6 questions we'll take, and then we'll end the session for today. But as I said, we assure everybody that whatever questions they have, and we have already got a list of them, we'll answer each of them individually after we take the answers from you, Mr. Sharma. So the first question is from Mr. Praveen Bonde. He's the chief engineer of the profession. And what he says is that, what are the qualifications required for the person to carry out UT test and routine survey? I'll club all these questions so you can answer them together. Any institute which gives training in UT, and how to get ASNT level 3 certificate. So these are the 3 questions which you can probably club and answer together. I think you already touched on some of this, but maybe you can just give a very direct answer.
Yeah, level 2 certifications are being done by many institutes. I don't know where you're located. If you're in Mumbai, there is a Mr. Bidde's institute is there.
I saw he is located in Amravati, so probably Mumbai.
Amravati also, if you check, there would be definitely some institute who would be providing, because now it is such a need of everybody to have certified people. So every small city or every place, I would say there are people who would be having this kind of trainings given and all. But there is in Pune also, there is one Insight NDT. Mr. Diwakar Joshi is running that institute, is doing a good job. And again, what is important is, as I said, the certification has to be as per the written practice. Or I would advise that since somebody has decided to go for a level 2 or a level 3 certification, why go for ASNT? You should go for either ISNT or a 9712 straight away, which has got more acceptance, and I would say international acceptance for those certifications, because these are central certification schemes. And very soon ISNT would be equivalent to 9712. They'll be issuing certificate which is as good as 9712 level 2. I think one should wait a little. Maybe by tomorrow I'll be able to give an update on that, what has happened. And I'm sure very, very soon this certification scheme will be available.
Okay, sir. Sorry, you have to add anything more?
And level 3 is for so many years, I did level 3 ASNT in 1987 when it was held second time in India. And after that, it was having the same routine, sometimes in Pune, sometimes not in Baroda, in Chennai, and every alternate year in Mumbai. And now I hear since 1 year or 1.5 years they have started conducting online level 3 training exams. So training is conducted by ISNT, also is one of the training for level 3 programs. BDA's Institute is one again who is conducting level 3 training programs, and the examination is conducted by ISNT, and which are now online examinations. So anybody wants to appear, they can study on their own and appear directly in the exam, or they can attend this training through ISNT or Mr. BDA's Institute, and then sit for the online exam.
Right. Thanks, Mr. Sharma.
Can I intervene just
Yeah,
a
sure.
second? We've been in touch with different, even Mr. Bhide, and we are planning to organize another theory session. Your session was very informative, and but it was in a compressed way. It gave hope, and it gave a sweet flavor in the mouth, but I think it left everybody wanting more. So
You gave me only this much time, sir.
so taking it forward, each of these topics, whether it is LPT, MPT, we can spend even 2 days discussing it totally in theory, and that actually leads to certification. So to answer Mr. Praveen Bonde's question, we would look, and we will try and provide an opportunity for all those who are interested, and we'll reach out to you within a certain period of time, and give you an opportunity to do level 1, level 2 if you're really up to it.
Can I suggest something which is better for the marine industry? It's just my opinion and suggestion. As I said, this certification ASNT is actually employers-based certification. So Institute of Marine Engineers being the apex body for all marine industry, they know what are the requirements of each one, either shipbuilder or the owner or the one who is doing some repairs, and all that is all known to IME as such. So why can't IME have a written practice which could be covering all those aspects, and then the certification could be done as per that written practice, which can be done by either BDA's Institute or somebody else, any level 3, seeing the written practice. They can conduct the training and examination as per the written practice, and that certificate would be, nobody would be objecting that this is not a valid certificate or the competency is lacking and all, because you'll be taking care of all the competencies that is required for various functions which NDT level 2 has to perform in the marine.
Very correct, sir. We will need to do it if we are doing it from IMEI. And
I will help you out. Honorary service for making a written practice, not a problem, sir.
So we'll take it up later, and we'll move on it.
Yes. Yeah.
Great. So that will help. We will touch base with you and then formulate something so that then we can offer to the people who are interested in doing it.
Yeah.
So the next question is from our colleague Sonali Banerjee, and of course who's part of IRS, which has been your company for so many years. And she wants to know whether we can do underwater MPI or NDT once underwater welding is done.
Yes, we can.
So and how? I mean, what is the process?
How to? There are some few service providers only who are doing, like underwater welding is also done. Now the operator goes inside through diving vessel or similar arrangement that you have on the offshore platform or on a ship, where the operator will go, and the interpretation part, the guidance will be given by the person who is there on board, and they would, maybe he can guide which areas to be scanned and which areas to be checked, even thickness where it is required, or even some other MPI or PT to be done, these kind of things, where it can be guided that this is the area where you require to do, and then you can give signals and interpretations, which can be, actual interpretation can be done by the person who is sitting doing the evaluation and monitoring the UT or NDT operator who is there. There are agencies who are doing that. I can get in touch with them and give a few names. There are people, but
I'm sure Sonali has also all the access to do that, being part of IRS. So I'm
in fact, their own department is into NDT services now, which during my time we didn't have that. Their safest, which is now part of IRS, they're providing a lot of NDT services. I know.
Right, sir. So there is one question by Royston Vaz. He says, what is the limitation with respect to porosity or depth of defect while doing the penetrant test?
Depth of defect again, it's like as I said in the code ASME section 8 division 1, up to 5 mm isolated pore is acceptable. If you get a 5 mm pore which is isolated, then that is the maximum size that can be accepted. If it is more than that, it is not acceptable. And similarly for aligned porosity or there is a cluster, the acceptance norms are given that, you know, cluster can be up to 1 inch cluster, and each diameter of the pore in that cluster should be how much distance from the next bigger size of pore, and these things are available and can be easily adopted. Again, what is important is he mentioned walls. Now you can directly apply ASME section 8 division 1 and appendix 8 if they are doing PT, and go by the guidance of acceptance norm that is given.
Okay, sir. There is one question by Mr. Ravi. How to prevent magnetic particle falling down?
Falling down from
yeah,
where?
that's the only. I mean, that's as brief as that. How to prevent magnetic particles falling down? So
actually, it has to. There is one of the important steps in the magnetic particle testing is like in PT, removal of excess penetrant. We have a removal of excess particle also. So we have in dry particle method, we are blowing not very high pressure, but with the blower, we are blowing air to see that the particles are thrown out, and only few of them are concentrated to form an indication, and there is not a heavy load of particles sitting to, you know, so that the indication doesn't form, which is formed is not visible.
okay,
particle has to fall off. We have to throw them off so that only few particles are available to form an indication.
Yeah, got it. I mean, I could understand that. Then there's a question from J. Remedios. Explain half-life period for gamma ray sources and what does it signify?
I explained during my this thing presentation. Half-life is the strength of the source become half. That is a half-life. As I gave you example also for iridium 192 source, the half-life period is 74 days. I mentioned. So 74 days means I have procured a source today, which is having a strength of 20 curies. Okay. After 74 days, without doing anything, the strength will become 10 curie. After another 74 days, the strength will become 5 curies. It keeps on depletion like that. If it is selenium 75, again, it has got half-life of 120 days. So after 120 days, 20 curie of selenium will become 10 curie, and like that.
Right, sir. There's a question from Satyakam Deepak Raut. He says, what are the practical applications of new technologies for determining the condition of paint-coated surface underwater? Paint coating underwater, how to, I mean,
under, see, paint nowadays for paint, you mean to say again for empty?
No, it's like the vessel is underwater, the paint condition. He wants to know that what is the paint thickness available, or what is existing at the moment, you know, with, I mean, after what, 2 years?
I think he's talking of not the metal thickness, but the paint thickness.
Yes, it's a paint thickness. Yes, exactly.
See, again, the paint thickness, metal thickness, how you're checking by using an ultrasonic thickness probe. And the paint thickness you're checking by having a eddy current probe. Eddy current probe is what is giving you the thickness of the paint. Even while it was painted onshore, you would have checked for a minimum thickness compliance by using a eddy current probe. So the same application which can be used underwater.
Underwater also. Right. Because probably you're looking at, you know, in case the vessel is not, they're not able to dock the vessel for some reason, like in COVID period, we are having an extended period where the vessels are trading. So then within the extended period, the paint should not get damaged, but ultimately, if it's down to bare metal, then we start having, you know, corrosion setting in and, you know, diminution of the steel. So that's what probably looking at as a solution, how we can make sure that at least it is intact so that there is no damage to that extent.
Even if the paint has gone beyond the minimum paint thickness requirement, in such situations, you will not be able to do anything. Only you will get the information that yes, this has happened. Now what next to be done whenever things.
Yeah, no, I mean, probably worst case scenario, you can have look at the emergency docking or something.
Yeah, yeah.
I mean, like our company now looking at doing remote dockings without superintendent attending. So it's already process is on. So things have changed dynamically, you know,
These are all the new opportunities which has come because of COVID.
yeah. We are just already one ship is in dry dock, just Great Eastern, which is without any superintendent on board. It's being done by remote. So
Yeah.
ultimately, that things have changed so much that we are, you know, we are situation where we are helpless.
Yeah.
Direction.
Actually, from offshore industry, I moved out in 1990 when I joined IRS. After that, I was into onshore construction, more of onshore construction work.
Right.
So I may not be able to, I have not answered to that confidence all your offshore related questions.
No, fair enough. So I mean, but at least since you have the knowledge and know-how, I mean, I'm sure that whatever is given is appropriate to what can be done. So there's one more question on from Sanjay Datta. He says, any new method to confirm cracks in the propeller bedding area?
New method.
Yeah, is there any? I mean,
these methods are generally which are used for detecting cracks are available. So new method, there is advanced eddy current which is now substituting certain parts of ultrasonic test. Edify is the company who are promoting this. Is one of the new methods which can be used if he is looking for a new method.
So it is the same principle or
that principle is again it is based on eddy currents. This is ultrasonic is based on sound waves. Sound waves. So that is also NDT method, but the principle is slightly different.
Okay. And there is one
not widely used in marine industry. Eddy current testing, people may not be so much aware of eddy current testing because that is not so much in use in marine. This is what I have seen. If I'm
any reason for that? I mean, is there any disadvantages which
no. It is generally used for tube testings and all, boiler tube testing, and when they're manufacturing and all generally it is in that area, it is widely done. So such a requirement like your boiler tubes, when you're procuring boiler tubes, maybe they are already eddy current tested before
sure.
Which is the manufacturers.
Okay, there is a question by Edmund Vaz. He says, any information available for NDT of hardness for crankshaft?
NDT of?
Crankshaft.
No, hardness, something mentioned. What?
Any information available for NDT of hardness for crankshaft? Emily basically wants to know how to check the hardness of the crankshaft in that sense. Because there's a minimal hardness beyond which you cannot use the crankshaft, you know, if it is softened because of some impact
or about hardness check.
Yeah.
The hardness check again. You have eddy current testing. Eddy current testing has got very wide applications where, you can check hardness, or you can check heat treatment, whether the part is properly heat treated or not. What we need to do is you have to fix the parameter, and then that against that parameter you fix, and then you segregate. It's called as segregation. You fix up a hardness what is desired, and you check the other areas. If they are not meeting the requirement, immediately you'll come to know that yes, this is a bit away, which can be easily identified.
Sir, and the last question we'll take for the day. Sorry, VK, you're saying something.
Yeah, we also have hardness testing machines.
Of course, yeah.
But that is completely.
Even portable hardness testing machines are available.
Yes, that we're using it. I mean, VK supplies to even for our company also whenever it is required. So, yes, for sure. So the last question is from Shoaib Mukri. He says, if there is any damage to hull plating and need to replace it, explain in detail how to carry out the job. How will you find which plate number? How to order the plate? How to weld? How to do the testing of the welding? So if you are able to have at least, you know.
Okay, I'll start with whatever information I'm lacking, I'll assume something and say so that you get my reply indirectly. So if you are renewing a hull plate, I assume, then firstly what you should know is what I should know is what is the thickness of the plate first of all. And first question what he asked is what is the plate number he can identify.
Yes.
If you see from the at the time of construction, what was the expansion, this thing of what plates were used at what location. Normally in the drawings it should have mentioned this is the plate, this is the location, this is the number of the plate, And based on that, what is the grade of the plate? That is also known from the drawing.
Sure, sure.
Once you know the grade and the location and the thickness, then you cut that particular plate. You know the grade always, and the
I think the more relevant question will be, if you don't get the plate of same thickness, then what bigger thickness you can go for, or whatever in that sense. So, is there a requirement for that?
If it is not,
I'm looking at it differently because ultimately all this is common knowledge, that how to get a plate, what plate, from where to get the access for the thickness of the plate. So I'm probably looking at, in case that same thickness is not available, then what is the next thickness you go for?
Generally, the same thickness would be available, but in case not available, the next 1 or 2 mm higher size would be available definitely.
Okay.
So that you will have to, again, because these questions are again 2-3 more. Procurement of plate, now that you know, like, you can one small plate, nobody will manufacture to your requirement. You have to go to a trader to get your plate and get it tested and see that it is meeting your requirement. Then you have to cut that plate to size, make the groove, because he has asked for how it is to be welded. Now you will have to make a groove on the plate. Is easy to make. Now the groove will depend upon what is the thickness, now which I am not knowing. If the thickness is less, say 8 mm or 6 mm hull plates, many times it is like that thickness, then there is no need to make a groove also. Inside you just do a grinding, you make a fit up with rounded corners. Corners have to be rounded, and then you make a fit up by grinding. The groove will be formed anyway from one side only. Then you use your SMW welding technique, and from the other side you do back chipping, dye penetrant testing, and then weld from the other side. And I don't think anything else is required to be done. I don't think it requires calls for any X-ray or NDT. If it calls, it is in a critical area, then you can do an ultrasonic test.
Okay. Sir, I'll take one last question because it's come. Here, there's from Praveen Chaudhary. He says, can piston ring coating be measured? The piston ring has some coating, so can it be measured?
What is how much is the coating?
Micromillimeters. I mean, it's just a coating on top of the steel.
But the coating thickness meters are available, no? This which work on the principle of eddy current test.
Yeah, because same like looking at paint thickness is how what the coating thickness is.
Yeah.
Right, sir. So then with this we will conclude today's training session. We would like to thank Mr. Arvind Sharma for sparing time to do this mini training session. As I said, this is only the start, and as Mr. Jain said, we'll be looking at doing extensive training for people who are interested. We will give the details in due course to the interested candidates. So I can only say that you have done a wonderful job in keeping the interest and sustain and enlightening us on the relevant aspects of NDT. Now, as I said, it makes us curious to know more about this topic. IMBA Mumbai branch is thankful to the training subcommittee for organizing this session with active support from the social media subcommittee. A special mention needs to be made of the behind the screen personnel who took all the efforts to make this possible. First and foremost, Sanjeev Mehra, whose tireless efforts and innovative ideas always make the session interesting and without glitches. Commodore Bhupesh Tatar, who is on the job round the clock. Mr. S.M. Rai, with all his experience, which is amply shared. Ms. Neeta, with her usual promptness to do what is required. Sunil Kumar and all the rest who contributed to make this happen seamlessly. Last but most importantly, we are greatly thankful to all the participants for being present in such large numbers, which has been instrumental in making the session a phenomenal success. Wish you all a wonderful evening and a relaxed Sunday. We now request all of you to stand up for the national anthem. Thank you.
So can we do a poll first?
Yes, Sanjeev, then we'll have to wait, right, in that sense?
Yeah, one second. I just launched the polling, sir.
It doesn't take time, actually. It will take just less than
a minute. Yeah. So maybe after 1 minute, let's stand and do the national anthem.
Yeah, after this is over,
yeah.
Do I need to fill this also? I don't think so, because
No, sir, you will not be able to do it because you are the host, but
Yeah.
other people, participants will be able to do that.
But all people who are not members of the IMEI, they are most welcome and encouraged to join. I think that is the idea of the first question. Whilst you're filling it up, I think we can announce that, especially for students and graduates, the fees are nothing much. And if you are a member, you would keep getting updated with all the happenings at IMEI, which, believe me, now are quite a few, thanks to the very active membership, thanks to the very active committee members.
And some of you, if you want to become a member of ISNT also, if there is an interest, they can become members. Like, in my last slide, I had mentioned the email info@isntmumbai.org.com, I think. So, or they can always send email and we can give you the forms.
Yes, anybody who's really serious into NDT is generally a member of ISNT. It's regarded as one of the best in the country. So, Sanjeev, are we done with it? Can we move?
Yeah.
I think we should.
Yeah. Okay. So
So
just waiting. So I'll share the results now. So you can see a lot of people who are not members.
Yeah, okay. We can
All right.
later.
Okay. All right.
Yep. So let's stand up for the national anthem.
Give me a sec, sir. Just let me get this. Right, check.
भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल गंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
So thanks again to IME for giving this opportunity. And
thank you so much for being here. And Sanjeev, can we remove the mute from everybody if it's possible?
Yeah, I can.
I can see a lot of IRS people who may have interacted with Mr. Arvind Kumar Sharma.
I didn't see the chat.
Okay, so people can unmute themselves now. They can unmute themselves.
Wants to reach out or
yeah.
Hello, sir.
Hello.
Please identify yourself if you're talking. You can.
Yeah, you can put your videos on and you can unmute yourselves.
Yes, sir. Hello, sir. Excuse me.
Please go ahead. Please.
Sir, can you share this presentation, please, sir?
It's already available with IME. You can have a PDF copy.
Yes, sir.
Please do write into IMEI and we can ensure it reaches you.
Okay, sir.
I suggest only a PDF copy. Maybe you can.
Yeah, we'll share the PDF copy only.
Okay, sir. On mail, or sir, or otherwise.
Yes, you can write in on email to mumbai@imari.in and you'll get it.
Sir, mail ID is
mumbai@imare.in.
okay, sir. Thank you so much, sir.
I have mentioned on the chat, Mumbai@IIM.in.
Okay, sir.
Right, sir. So can we close, sir?
Sir, excuse me, sir.
Please go ahead. Identify
Sir.
yourself.
Okay, sir. This session was a very most important lecture for myself.
Identify yourself first, please. Who's speaking?
I am from Great Eastern, sir.
Yes, but your good name.
Cadet. Myself, Sagar Tunnel.
Okay. Please go ahead, Mr. Sagar.
Yes, sir. I am very interactive about this topic, NDT and all of UT and radiography and all of this. This is a good session for I experienced very well, sir. Thank you so much for this, sir.
Thank you so much, Sagar.
Thank you.
Very much.
I think we can end it, I guess.
Yes,
Okay, sir. Okay, sir. Okay, sir. Okay, sir.
Thanks, Mr. Sharma. Thanks.
Bye and take care, all of you.
Okay. Thank you so much, sir. Arvind, sir.
Okay, ji, thank you very much.
Stay